Okay, this chapter is going to be on Newton's second law of motion. And the simple way of thinking of Newton's second law of motion is simply the harder we push on something, the faster it's going to move. So if we kick something really hard, it's going to move very, very fast. If we kick something kind of gently, it's going to move slowly. And so we'll get a little more specific about that. But generally, it's just the harder you push something, the faster it's going to move. All right, so let's look at that. It's going to be force and acceleration. All right, so the harder we push it, I said move before, we're going to get a little more specific here. The faster it's going to accelerate, all right? So if you don't have any force, if there's no push at all, there's zero force, then there's no acceleration, all right? So no acceleration can mean that the object's not moving, or no acceleration can mean that an object is going down the freeway at a constant velocity type of thing, or it's floating through space at a constant velocity. Until we apply a force, then we will have acceleration. When we apply that force, we no longer have zero force, we now have acceleration. And we can define the acceleration, remember, as a change in velocity over the time interval. So if you remember, change in velocity, that'll be meters per second over your time, so we end up with meters per second for acceleration. That's the definition of acceleration. We've already seen that. All we're looking at here is applying a force and seeing that it changes your velocity. A force applied will result in acceleration. All right? So when we look at it, if we have a net force, okay, a net force, some force, that's not zero, we are going to accelerate this object. So if we have a force and we have a velocity, that it can't be constant because we've just applied a force to it, the object's going to accelerate, all right? So anytime you have a net force on an object, it's going to accelerate. And net force, we're going to look at different forces acting on it. So what I mean by net force is that you don't have, you know, one person pushing on one side of the block and another on the other side. That could net out to zero. You'll see zero acceleration. We can have friction that's greater than our force applied, and then you will not see acceleration. If the friction's too great, if you push ever so slightly on a book sitting, or your computer sitting on the counter, it won't move at all. There's no acceleration. You haven't passed that force of friction yet. So we're looking at net force when we look at acceleration. All right, so basic summary of this is the bigger the force, the greater the acceleration. So a small force gives you small acceleration, and a large force gives you large acceleration. And when we talk about it mathematically, we are going to say these are directly proportional to each other. It's not an inverse proportional ratio here. It's going to be directly proportional. Small force, small acceleration; large force, large acceleration. Okay? So, and it's actually, there's no coefficient. They're just, if you double the force, you're going to get double the acceleration. If you triple the force, you're going to get triple the acceleration. And when I say this, I'm assuming it's on the same amount of mass, right? We're not changing. We're not suddenly making our boulder twice as big in this scenario. So if we double a force on the same exact book or the same exact computer as we push on it, if we double it, we'll double the acceleration. Okay, so let's do a quick check. It's in gray. You don't have to write it. You push on a crate with 100 newtons of force. If the friction of force is 100 newtons, does the crate accelerate? Well, here's the fun thing about friction, is friction always opposes you. I know people who are like this. They always oppose. You could say, let's go to lunch, and they'll be opposed to it. Friction's like that person. That it's always opposed to whatever direction you try to push. You push from left to right, friction opposes you. Right to left, friction opposes you. Doesn't matter which way you push, it is opposed to it. So if we have a net force here, we're pushing one direction with 100 newtons, and the friction force is 100 newtons. We know that's in the opposite direction because that's just friction. So your net force here is going to be zero. You're going to end up with zero acceleration. Okay, does that mean the crate is not moving? Well, that becomes an interesting question. There's no acceleration We weren't given in this problem whether there was already some velocity. Maybe that guy's been pushing that crate for an hour to the right and it's sliding along just fine. He adds another 100 newtons of force, gives it a push, and there's 100 newtons of friction, and so there's no acceleration and there's no change. He's just cruising along whatever direction to the right here. All we know is that from this scenario, all we know is that there's no acceleration. That block could be, floating through air. Maybe he's on, an ice rink with very little friction. I don't know. It doesn't matter. What we know is the force applied was exactly countered by the friction, so we didn't accelerate anything. All right, now we push with 150 Newton friction is still 100. Now does the crate accelerate? And so you can see our push is greater than the friction. And so now we talk about acceleration. Now we are clearly going to accelerate, and we're going to accelerate in the direction of the push. Okay? And then remember, if we double the force on the same mass, what happens to our acceleration? That was a couple slides. Okay. Now let's look at mass and weight. And I know we've hit this a little bit before, but mass is the quantity of matter in an object, and weight is the force of gravity on that object. So if you want to lose weight, you just go to the moon, you've lost a ton of weight. You're not any smaller, you don't fit your jeans any better, but you've lost your weight. Your mass, the amount of matter in you, is exactly the same. So whenever we talk about weight, we're always talking about it in relationship to gravity. We always need gravity to measure weight. Right? Mass is universal. Wherever you go, your mass remains the same. You have the same mass in outer space as you do on Earth, as you do on the moon. Makes no difference. The weight will depend on where you are. You could be weightless, and you will still have mass. Okay? So mass is the measure of inertia. If you remember the previous lecture, it's inertia. The metric unit for that is the kilogram. You should know that. Metric unit for weight is the Newton. And the Newton is very similar to the pound. If you want to think of it like pounds, you can think of it that way, but you need to do the math as if it's a Newton, okay? But if you want to think in your head, well, that's like the pounds. But mathematically, we're going to be using the Newton. Okay, so back to our little scenarios here. If you hit something with the same force here, okay? Same force. You hit something that's small, you're going to get a larger acceleration because it's small. If you push on a little pebble, you get it to move faster. All right? When we look at something larger, or bowling ball or something, that same push will do less to accelerate it. All right, and you guys know how much I love Hewitt, and you know how much I love the book, and there is an instructor manual that goes with the book that is associated with these lectures. And what I really love about it is in the instructor manual, it actually suggests the teacher lie down, put an anvil on their stomach, and hand a sledgehammer to a student to hit the anvil so that you could see the inertia of the anvil will make it so that the sledgehammer doesn't squish me. And if you think I'm crazy enough to give anyone a sledgehammer, then you've lost it. There is no way. This demo, at least it's possible. I still don't think I'm going to do it, though. It's the same idea, though. If you had a force applied to your little nail, if you put a ton of books there, then that mass, you make it very massive, right? Instead of just having that little piece of wood, a small mass, you increase the mass by adding all these books. You'll feel it a lot less because the acceleration onto your head is going to be a lot smaller by making the mass bigger. Still don't think I'm going to try it, but you get the idea. All right, for a given force, the greater the mass, the smaller the acceleration. And this is going to be inversely proportional, but it's still going to be sort of a one-to-one thing. So double the mass, you get half the acceleration. So it's inverse, it's exactly inverse. Triple the mass, you get a third of the acceleration. Half the mass, you get double the acceleration. So again, mathematically, that's inversely proportional. All right, so just checking. Top left up here, we have the force of a hand accelerates a brick. We are assuming no friction in this, all right? As we go down that left-hand column, the same force accelerates 2 bricks. So does that go just as fast, half as fast, double as fast? Remember the previous slide? The same force accelerates 2 bricks. Okay, and then go to the next one. If it's 3 bricks, how much acceleration? And hopefully you're remembering that the same force would accelerate 2 bricks at half the acceleration, and it would accelerate 3 bricks at a third. Remember, it's inversely proportional. All right, now the right-hand column, go again, look at the top of the right-hand column here, and you have a force of a hand accelerates a brick, just like the left-hand column. But now we're going to increase the force. See, we got 2 hands on it, so we're going to increase the force, twice the force on the same little 1 brick. All right, so if you have twice the force, you should get twice the acceleration. All right, and then the very last one in the bottom right-hand corner, you have twice the force on twice the mass. Okay, so we've doubled the force. We have 2 hands, but we've also doubled the mass. So you are going to have no difference here. The acceleration is going to be the same on the bottom right column as it is on the top right column, because doubling the force, but we've doubled the mass, so we've lost any advantage of doubling the force. All right, so when we want to kind of get it all together, we start to put it in equation form. The acceleration goes as a net force. Okay, acceleration goes as inverse of mass, and acceleration only depends on force and mass. There's no coefficients here. There's no squaring of anything. So it's a pretty simple formula. It's going to be acceleration equals the force, the net force, over the mass, right? We don't have any numbers. It's pretty simple. There's only 3 variables in that. And the acceleration is always in the direction of the net force, because remember, these are in fact vectors. So let's look at it. These are just some examples. If you have a spool and it's sitting kind of far away from you and you want to get it towards you, you pull on the string. Which direction does the spool move? And we have 2 different scenarios here. We have the pool has the string looped over the top and you're going to pull in this direction. Or what happens if the spindle's upside down and the spool, it's underneath, and you're going to pull on the string this way. All right, so what's going to be the difference? Well, just go to basic physics. We are applying a force in this direction in both of these. Does it matter which way it's looped? The force here is applied in this direction, and the force here is applied in this direction, which means in both scenarios, the only acceleration is going to be in this direction. So it doesn't matter which way the string is. The spool will move to the right. All right, so, and these are different chapters in your book. I didn't catch that. From chapter 3, we know acceleration of gravity on Earth is 10 meters per second squared. I think that's chapter 2 in your book, but don't worry about it. So we know it's 10 meters per second squared, and from Newton's second law, that's this chapter, the force equals the mass times acceleration. We had previously written it as acceleration equals force over mass, but we've just rewritten it here, right? We can move these around any way we want. Force equals mass times acceleration, so now we can do some examples. Force is going to be in newtons, all right? So if we have 10 newtons, and we have 1 kilogram of flour of, I don't know, nuts here, the acceleration of gravity is going to be 10 meters per second, and remember that is always down. Doesn't matter. Gravity is always down. I know I sound repetitive when I say it, but in some of these complicated ones, it's good just to remember that. So that means that from this formula, we can figure out that anything that weighs 1 kilogram, if we say, oh, well, not weighs, mass. The mass is 1 kilogram of an object, then we know that mass is 10 newtons. We just figured that out. Here on Earth, all right? Here on Earth, something's 1 kilogram. We can call that 10 newtons. Okay, so let's say you are carrying a bowling ball in a grocery bag. How much does the bag support? Well, if it's 6 kilograms, we know we can do the math. We're assuming this woman is walking on Earth and not on the moon. So that should be 6 kilograms times the acceleration of gravity, which is 10 meters per second squared, down, and we should get 60 newtons. All right, so hopefully that'll be 60 newtons straight down. Now, here's what we have often found in life. You can kind of hold something in a bag if you're really gentle with it, but if you jerk it up, all of a sudden that bag breaks, and you go, well, hold on, my bowling ball didn't get any heavier, or my milk, my milk cartons didn't get any heavier. Why did my bag break? Well, by accelerating your bowling ball upwards, by accelerating your milk cartons upward, you've applied an additional force. You made that bag do an additional force of, now you have 6 kilograms times 5 meters per second squared, so an additional 30 newtons of force onto your bag. This is just like when you go to weigh yourself and you're standing on your scale in your bathroom and you jump on it. That isn't your true weight, but that is the weight you have applied, the force you have applied to the scale. By jumping on it, you have accelerated, and that scale has to stop your acceleration. It has to do like a negative, a decelerating effect, which will read as pounds on the scale. Same idea. Anytime you jerk something, anytime you move something and accelerate it, you are applying a force. Remember, we have to find the net force on things. Net means we have to add all the forces up. The force of it just being a bowling ball in a bag, just regular gravity. And then the force if she decides to move it. We have to add all those up and get the net force of an object. So let's think about what happens in an elevator. If you've ever been in an elevator, and you know when the elevator decides to go up, right? If you're going to go up, if you accelerate up, you are going to feel that acceleration as if you are heavier, all right? And then if the elevator accelerates downward, okay, and it's going down, you will feel as if you're lighter. And then the very far one is free fall. If it's going down at 10 meters per second squared, this one over here is free fall. You are falling down at the rate of gravity. You would read a big fat nothing on that scale because you're in free fall. So let's think about over here. If you have something that's 1 kilogram, we know that's 10 newtons normally at 0 acceleration. As you accelerate upward by half of that, 5 meters per second, this should actually get heavier by 5 newtons. So that should read 15. This one should actually get lighter by an additional, or by 5 newtons, so that should read 5. This is going to read a big fat 0 over here because it's in free fall. So there you go, and there you go. All right. All right, let's look at Newton's second law and free fall. So when we think of free fall, and we're taking away air resistance here. Remember, this is going to be Galileo dropping the masses off the Leaning Tower of Pisa, right? We're going to drop masses, and we're gonna measure how fast they are. And it's hard to imagine why something bigger doesn't fall twice as fast. But in here, okay, on these equations over here, G is acceleration, right? G is so special. Gravity's just so near and dear to us that we give it its own designation as G, but that's really just A for acceleration, right? So let's look at it. If we rearrange the formula, we get force over mass, all right? And if we look at this, we go, well, there's, a force on this mass here, and it's going to cause it to fall with gravity, okay, at a certain rate. We know that's 10 meters per second squared, but let's just look at the ratios here, all right? So we have a mass. Well, we made that mass twice as big, okay? Well, all right, we made the mass twice as big. The force is twice as much on it. That force of gravity is twice as much on it, but look at it, it's a ratio. So if you make something twice as big and the force is twice as big, those two cancel out to 1. I can make this 100 times as big. And I could have 100 times my mass here, and I'll have 100 times the force on it, but 100 over 100 is still just 1. So it doesn't matter how big we make it. It's a ratio like that. It'll always accelerate at the same rate. And that is because literally of this formula. You can add mass to it, which adds force, but the bigger your force, the bigger your mass, they cancel out, right? I mean, you guys are used to, you're used to fractions doing that. All right, so let's look over here. Same idea. You have a boulder falling. Now, when you look at the feather, you have to remember we're taking away air resistance. All right, no air resistance. And the boulder and the feather, and you can actually do this at, in San Francisco at the Exploratorium. They have a feather in a vacuum tube, and it falls, you know, right away. But the boulder and the feather are going to fall at the same rate. The feather has a much smaller mass, but it also has much less force on it. So acceleration is going to be the same. And yes, the boulder does have more force applied to it, but it has a bigger mass, which means it's harder to move it. Remember the basis of inertia? It's hard to move something. Well, the harder it is to move that boulder, you know, the less it's going to accelerate. So yes, there's a bigger force, but it's not going to accelerate it more than it accelerates the feather. And you can see this, like, y is, even however big your ratio gets, or however big your circle gets, excuse me, for a circle, the ratio remains the same, and it's because it's a ratio. Ratios will do that. So if you're looking at C over D for the pink circle, or C over D for the little green circle, you know, that's circumference over diameter for pi. Yeah, the pink one has a bigger circumference, but it also has a bigger diameter, so it all comes out in the wash. All right, so like I said, the Exploratorium has this little demo. With any luck, we'll get to go see it. When there's air in the tube, the feather falls slowly, but if you remove the air and it's a vacuum, the feather and the coin will fall at the exact same acceleration. All right, and you can try this. This was supposed to be in gray. I apologize. You don't need to write this down. You can try it. If you drop a sheet of paper, it should fall very slowly. And then if you block the air resistance and put that on a book, hopefully it stays close enough you don't get air resistance, it'll fall much faster. And that's just by reducing the air resistance. Oh, so let's look at friction, that lovely force that opposes everything you do. When we talk about friction, we generally are referring to solids, like any solid surface. When we look at air resistance, then we're talking more like the fluids, the air. I will tell you this idea, whether it's air resistance or friction, they're all pretty much the same problem. You have these molecules, they get in your way. They're slightly different, but they're really similar. Friction will always oppose you. Air resistance always opposes motion. You can get the same thing in water where you have fluid and you try to have a boat going through it. You're going to essentially get friction there that slows you down. So anytime you're talking about matter and molecules, you're going to end up with this problem. So let's look at friction. Obviously, the rougher the surface, the greater the friction is, and the smoother it is, the less it is. And we can even talk more in depth. We can talk about something called static friction versus kinetic friction, which is static friction is how hard it is to push something when it's at rest, to get it going, right? Just to get it going is really, really difficult sometimes. But once you're going, you're like, this is easy. Well, that's because friction actually changes when it's static, when it's just a block at rest. It's hard to move it, and as it starts to slide, that friction actually is a different kind of friction. So friction actually gets kind of complicated. It's one reason why you never want to lock up your wheels when you're driving in skid, because again, static friction is greater. Think again, it's hard to get something moving. Well, when your wheels are turning on the road, that's actually static friction. I know you're thinking, well, that's crazy because my car's moving, but the wheel's actually turning. So between your tire and the road, it's not moving, we hope. We hope that's stable. But when you start to skid, if you start to skid, then you move into kinetic friction and you actually lose traction. It's actually less friction when that wheel is skidding. You don't want to skid. You want your friction to stay static. You actually get more friction that way. So you want your wheel always turning and touching the road that way. You don't want to lock up your tires and then skid, because you will lose control, because you'll actually take longer to stop as well. So if you're just looking at how long it takes to stop a car, if you lock up the tires and you have this what's called kinetic friction, you're actually going to slide farther. All right, let's look at air resistance. And when we talk about, drag of the molecules of a gas or a liquid, all fluids do this. Water, milk, oil, doesn't matter. There's this sort of resistance to things moving through them. And so you end up with this drag force. What it depends on is going to be the area of the object, right? It's size, and here I'm talking volume. I'm not talking mass. I'm talking volume. It's the area that encounters the fluid, and the speed. The larger the speed, the larger the drag. So, if you kind of just swoosh your hands gently through the water, it's all nice and lovely. And the second you try to move quickly and shove your hand through, all of a sudden you feel that resistance. That is because the resistance literally goes up, mathematically literally goes up the faster you try to move through it. Isn't that fun? All right, so let's look at air resistance on a falling object. So we have gravity pulling down, and then in this diagram that's listed as weight. A lot of times you'll just see mg there. It'll be mass times gravity, but we know that weight is a force, is the same thing as mass times gravity. So we have the arrows pointing down, you have the free fall pointing down, but you always have some kind of air resistance here, all right? So as you look, as this person is falling, the top diagram has very little air resistance. That means she's moving kind of slowly, and the air resistance increases as she moves faster. And then in the bottom diagram, you can see the air resistance and the weight, her mass times gravity, her weight there, have equaled out. And we have a special term for when the air resistance and the weight equal out. Okay, we call that the terminal speed, and what that means is that's as fast as you're going here on Earth, right? You're not going to fall any faster than your terminal speed. So, and it'll depend on the drag force and the weight here. So every person's going to have a different terminal speed, but basically what it's saying is when the air resistance equals out the weight, right? That mass times gravity equals that out, then you have reached your terminal velocity, your terminal speed, terminal velocity. You're not going to go any faster. That means you're not accelerating anymore. You are still probably going very, very fast. It's a high velocity, but you're not going to accelerate anymore. Yeah, this is all grayed out because you don't have to write any of it, but it is kind of funny. And no, I'm not actually going to drop a cat for a demonstration because that's just plain mean. But when you look at the terminal velocity of a cat, they actually reach terminal velocity fairly quickly, which is why they survive these really long falls. If you drop them, I think it's over 6 stories or so, they don't go any faster after that. So you get, 6 stories. You get the same terminal velocity at 35, 40, doesn't matter, stories, as you would from just falling from a 6-story window. And believe it or not, they can kind of survive that, which seems crazy to me, but they do splay out, which is why they reach their terminal velocity quickly. They do try to just increase their air resistance. So I just thought that was kind of funny. Again, it's grayed out. You don't really have to write any of that down.